Okay, and we're started. So hello, everyone. Thank you so much for joining the Computer Over Data Working Group session. This is our first time getting together as a community after the excellent series of events in Lisbon a few weeks back, earlier this month. Before I hand over to our first presenters, I want to just share a couple points of reference here. If anyone has follow-up discussions, questions, or wants to share documentation for their project, please jump into the Slack link here for the Compute Over Data Working Group. That'll take you to the Filecoin Slack server and the Compute Over Data Working Group channel specifically, which is also a public channel. So you do not need anyone's permissions to be added there. We are also keeping track of the recordings here at codsummit.io from the summit. And then also in the Slack channel is a link to the full broken down speeches, which are available by speaker. So I'll repost that so everyone has it available. Now, first on our list today is going to be the Nunet team. And so I'm going to hand it over to Kabir. And Kabir, whenever you are ready, I will let you share and take us through an overview of Nunet.
All right. So we are Nunet, and we are building a global economy of decentralized computing. This is our slogan. And basically the concept is that we want to build economy of hardware, software, and data where all of these entities, let's say, interact in a flexible, decentralized computational universe, which is basically can be described as some sort of decentralized hardware, software mesh without central point, of course. So that is, I think I will start with a vision, what we want to do, which is can span over, more than 20 minutes. And then I will try to explain what exactly are we doing and what kind of things we have and try to run a small demo. So basically, what does that mean? That's like in terms of vision, what we want to have is, or we want to build is in evolving decentralized computational universe, meaning that software agents can find other compute resources to execute themselves and pay for the execution costs themselves, knowing what are those execution costs and knowing the place in the business model. Then hardware resources or agents can advertise their capabilities so that other components in this whole ecosystem or whatever computation universe can find them in the network and send requests, receive responses. We want to integrate data sources which can declare the data content and price this data so that software agents can buy data points or data sources pretty much based on the declarative knowledge of what this data does for algorithms. We also want to integrate developers so that they can publish the algorithms as software agents, declaring the capabilities of those algorithms and the needs for compute resources so that the whole thing also becomes an evolving ecosystem of algorithms. Software. Then application developers could construct the backends on these applications of the applications based on all this infrastructure that we would build, algorithms running on their own, let's say, paying for the compute resources. And the Nunet platform, the thing that we envision in the Nunet platform as the main thing is that it constructs automatically this network of algorithms, machines, and data sources, considering basically the places topologically, topographically, etc., and so on, based on the requirements of the certain compute processes or even individual calls to the platform. So basically, there was a question: what problems Nunet solve, and that is a kind of a complex one because there are many things, basically many opportunities. So to kind of make it short, it's one of the problems that we want to solve is utilization of latent compute resources, because there are a lot of compute resources around the world which are not utilized because everybody is using data centers. And that could be achieved by building this connectivity of devices of different type locality from different vendors, running different software, etc., and so on and so forth, in some kind of single decentralized cloud. Single, which means they are connected, but they're not managed by a single entity. And this is a, let's say, assumption, which is not, based on certain research and in a space that by building this cloud, let's say decentralized cloud based on the principle of decentralization. Just by design, we can develop better robustness and security of the computational universe than centralized approaches can even imagine to offer. There's a lot of work there. It's not something that is given by just for free, but there is a potential that we want to tap into. And so what we want to create machine-to-machine economy of what I mentioned, kind of hardware/software mesh or cloud, and the self-optimizing compute engine, which could automatically optimize hardware configuration topology based on immediate requirements for compute, which means for software and where data is, and of course connectivity topology. So basically, what we are looking for as a kind of use cases, as a classes of use cases, is global hardware decentralization layer for Web3 platform application, or Web 3.0, depending on where you are in this kind of terminology. And basis for novel and previously impossible, as we see it, Industry 4.0 and IoT application, which is basically allowing business models to run on this framework, and kind of bridging the world of business and economy to the open source platforms. And this is a kind of far reach, is the platform for algorithmic governance of decentralized autonomous organization, which is something that we are looking forward to integrating into the governance of the whole platform. So just a little bit of history. Nunet is a spin-off of SingularityNet global AI marketplace. We were incubated as a small team since 2018. We got spinned off as a separate company in 2021. We issued our cross-chain utility token, which is one which we are going to use, or building the usage for it to power the whole economy and to do the settlements in the network. Well, currently, we are 20 plus team. Most of them, well, more than half of them are developers. So I will skip all the rest. Now, in terms of the architecture, well, conceptual architecture, basically we're building a layer between, as I mentioned, software and hardware, with a layer of location, context, awareness, mobility, communication between hardware and software, and between hardware and software, and the payment layer, so that all these components, which can come from different owners, different entities, etc., could also integrate in economically, meaning exchange value between each other and basically pay for each other for the work. Now, in terms of the ecosystem, so basically we integrate data providers, or we aim to integrate data providers, which is data, compute providers, hardware, algorithms, which is right now, as we are SingularityNet's spin-off, we are looking to SingularityNet, or we are not constrained to that. Consumers of applications themselves, which are business models themselves, and application developers. So at certain point, we would like to kind of construct this way of people to use Nunet as a backend and to monetize. Basically, we're looking for being able to monetize each call, depending on what kind of hardware and what kind of software is running. So just some kind of short/long list of what we want to achieve in terms of tech. So autonomy of hardware and software agents or nodes, context awareness, meaning that basically, or computational reflection, basically that every node should understand its place in the topology based on where it is, what is data, what is the latency of connections, etc. and so on. Computational reflections, in a sense that algorithms, basically what we want to do a layer where algorithms could understand to a certain point on what hardware they run, on what kind of hardware they need, and how much does that cost, and sort of make the decisions more or less autonomously how to select that, and vice versa. What kind of software, hardware is running, and how much it's sort of rental. That, which is some kind of making all these entities as a first-class citizens with a certain, let's say, level of intelligence within the network. Mobile computational process, meaning the processes should be able themselves to port to wherever place they want to be in the network in order to make this optimized. Value exchange between data computing, hardware, etc., and also payment settlements layer. Logical scalability, meaning that basically each agent in the network should be able to spawn and to ask other agents to do work for that. Now, collective verification, validation, security, these are sort of requirements for the platform that we want to build in. And I mean, I could put a question mark there, but the collective means that we do not want to become any central point of who, let's say, does the verification, who does validation security, where the whole Web3 sort of space comes in, and blockchain, at least conceptually, comes in with the concepts. Yeah, so we are building an open source platform allowing to choose permission level, which means permissioning level, which means we would like to open it up for the commercial usages, which means we do not really want to prevent proprietary code that runs on the platform, but we want to keep the platform open source completely. Decentralized ownership, yeah, meaning that every machine in the network and every algorithm in the network can be owned by different people, different entities. So from the kind of the basis of how we try to build conceptually the model is that we kind of take the actor model for computation as a guiding model, let's say, which means everything is an actor. And yeah, I will skip that part, but let's take it for that. But basically, this is a computation model of the Nunet as a platform. Now, from a certain sense, it's a self-organizing graph of different entities connected together via certain APIs that we're building, or we aim to build. From another sense, we can say it's serverless-ish. I took the ish from, I think, David's presentation some time ago, which nothing is serverless completely. Serverless workflow orchestration. Then we want to basically build this layer of declarative searching and matching between all the agents across each other, which comes to a kind of research project level thing, which is AI DSL, which we call AI domain specific language, which is general purpose description language for AI engines or software in general, hardware and data. So we cannot really think that we can build this immediately, but I believe that we can build it iteratively from the manually constructed, let's say, DACs, which define programs and hardware requirements, etc., to certain let's say, making it more and more intelligent as it goes. So opening up for the algorithms themselves to choose hardware, or maybe to choose other algorithms, etc., and so on and so forth. So the things that, well, it's a little bit not completely, let's say, ordered list. So what we are looking for as certain aspects of the system, and it's a little bit things can be missed here because it's pretty huge. So pseudonymous identity management and authentication system. We're looking to research basically. Here is part of research that we're looking forward and try to look for the partners to build it up. Pseudonymous identity management authentication system within the network. Authentication means ID. We need IDs and sort of identification of each machine or each node in the network. So it's not only humans but also them. Concurrent reputation systems, which means we want to build a reputation API which should allow reputation system to interact between each other rather than building one reputation system which is supposedly have to know everything. A tokenized data fabric mesh with a metadata which describes metadata so that algorithms could choose what kind of data they can use for the purposes of the whatever computation they're doing. Caching of compute state, this is something that we need to solve, and looking forward very much to the basically IPFS or partnership with the ecosystem to solve that. And we are looking to all kind of to run all kind of applications, including long-lived applications which just need to be hosted somewhere, and also domain naming system and direct access to all this platform from the usual internet, HTTP and addresses. So basically what we are, as I said, what we're trying to do, first of all, we are building a backend where you can just drop a DAG, either manually constructed, which defines your basically logic of the backend that you want to run. And given that we have all those algorithms onboarded onto the network, we simply can dynamically construct it and run this. And based on the use case requirements of latency, etc., and so on and so forth, we can provide, or at least this is aimed to provide the answer to front end, whatever the application. And we would like in the future to reach certain stage, which is probably long-term vision, is where we can build those DAGs dynamically based on certain intelligence which is in the network itself. So we call it a kind of AI DSL project. So the way we are building it, we are building open API, what we call open API of APIs. So the whole functionality of Nunet platform, we define it as a collection of open APIs and of each component within the platform. And we do this APIs publicly available. And then we try to develop the platform ourselves, like on the basis of those APIs. And also we are exposing everything to the community, whoever these are, people who want to use the platform or people who want to integrate, or the platform integrators, so that we can develop based on the same, well, let's say coordinate the development within the ecosystem. So the lifecycle, basically, as I said, is defined by this open API of APIs. I think I have to follow. I will publish this. I will send this presentation so that you could go follow the links. But basically, we yeah, let's say this one. We the APIs on the basically, I think it's a sync API specification. And then we publish them on one hand, we publish them as, yeah, for everybody basically to see and to describe things. Some of things can be just requirements for certain functions to be implemented. Some of the things are implemented. And let's say the goal is then so then we implement those functions and calls, what we need for our integrations against those API specifications. So let's say this is, I think, the example of Cardano contract implementing certain endpoints. We build infrastructure that needed for that integration. And then what's kind of, well, not most important, but we test all the platform and we integrate those, like testing of API calls into CI/CD pipeline. And we build this CI/CD pipe, or we run this CI/CD pipeline on the community sourced machines, which more or less resemble the network that we want to run in the production. So in this sense, we are basically constructing the process where we can integrate different aspects of the platform, including, let's say, our own aspects that we are trying to build, but also what we would like to integrate from the larger community, so that it becomes a trusted place where yeah, we can to a certain extent know that things are running.
And Kabir, just a little side note. This is excellent so far. If you could wrap up in maybe 2 to 3 more minutes, we'll pass on to the next group. But I know you got a lot of content, so thank you.
I think I will skip it, but basically that was an image that I think I did like 3 years ago. So this is what we want to get. We want to build this API of APIs, which connects to different platforms in the space. And since we want to provide also the tokenomics, which means value exchange. So yes. Now this is design, so I will skip that. Now the way we are developing is what we call use case-based platform development model, which means we are integrating use cases and we're building features of the platform based on certain use cases that we already see in what can be used, what the platform can be used for. And therefore we are looking for both platform integration partners, meaning platforms that, or solutions that can run certain things, well, based on what I said, and integrate into this, let's say, based on this API, and also, or API of APIs, which hopefully we can develop collaboratively, and also use case integration partners where we are looking for business models and real world users that can already be used on whatever level of the platform we have. So we try to bridge the two and to find the sweet spot of the next step of the development that we can reach. So I guess I will skip the use cases and prototypes. These are the use cases. These are prototypes that we have built. These are use cases that we are building right now. We have a bunch of things. Now, one of the things that I wanted to say, so we are building blockchain integration. Right now, we are building it with a Cardano blockchain, but basically we are blockchain agnostic, meaning that if we see that we need to do certain settlements between the agents, we basically expose this. I mean, we build this tokenomics API. We expose this via each component in the network, which basically we call it DMS, or the device management service. And yeah, we allow everybody basically to use that. So then we just a few days ago, we launched a testnet network which is right now, it's a Discord server, but that's not the main thing. We are sort of expanding our development from the development team to the community, where people could not only kind of give us intelligence what is needed, but also collaborate in order to let's say do the bug request or sort of feature request and introduce the code. And I mean, most importantly, to test certain use cases and to provide devices to run the network and to test how it runs. So right here are our demos and links, and now I believe I may try to run a demo, which is
yes. And Kabir, I apologize, just given the time crunch, would you mind if we scheduled a future session to do a demo for Nunet, or
sure.
posted a link as a follow-up?
Yeah, it's just a kind of demo that we have something, but I think the main thing is what I was showing. What we are looking for is basically collaboration with the community. So I would invite to get in touch with us and to try to connect, and we are trying to kind of categorize the community in order how to collaborate with on the platform integration level, on the use case integration level, and to sort of build up this network where we can actually develop things based on that.
Very good. Thank you so much. And normally we would save some additional time for Q&A. I think there's probably a lot of questions people have, because I really like your guys' architecture on the APIs. But at a minimum, we will post all this information in the Slack channel. And then if we can get a recording with you guys, we might post that as well, or maybe schedule you guys for a future session. I'm thinking 30 minutes is a better fit for some of our presentations.
Of this session, it would be excellent. We will just propagate it for our network.
We'll keep doing some more. All right. Well, so transition to our next set of speakers from Boutian and Derek. Are you guys ready? We'll take us away when you're ready.
Sure.
All right, I swear I know how to use technology. Okay. All right, so I should be unmuted. You can see my slides. I'm just going to share one screen. I don't know if the share two, it's broadcasting both at the same time, but just so that it's readable. So hello, everybody. Thank you for giving us the time today. I'm Derek Anderson of Blockless. One of the members here, Boutian, is also here, so I'll give a quick introduction about myself. Been working on the internet since the mid-90s. I did a stint at Big Fortune 200 from PayPal, eBay, LG Electronics, Walmart. I've got a couple patents around security and consumer electronic security sandboxing, and basically have been working in Web3 for about 3 years now. You may be familiar with one of my alma maters, which is Akash Network. I was there for about 2 years before switching gears and joining this team. We have a little bit different vision on what we think Web3 will be, and I'll let Boutian go ahead and introduce herself since she's around.
Oh, yeah, sure. Hi, everyone. Great opportunity that we have to here to present Blockless. Previously, my first project that I did was Wabi, which was back in 2017, and later on, moving to also investment side of Web3. And the team right now, we have 13 people full-time working on Blockless. and a couple of engineers themselves are entrepreneurs, former CTO on their own, used to run projects backed by layer one ecosystem as well. We are spread all across the globe. Majority of us in the US here, Derek in South Dakota, and then a couple folks in the Bay Area, while the rest of the engineers in India and China.
All right. So exactly what problem is Blockless solving? And I think we're all kind of, part of this group, compute over data. So we're obviously all kind of looking at some of the similar problems in this space. And really, we're looking at scalable and fault-tolerant systems, especially when it comes to compute. We want to be verifiable as well. And so that's exactly where we're kind of looking at moving our compute layer that we're working on. The special thing that I think that we're trying to also do is we want to kind of abstract the scalable and fault tolerancy away from the developer that's actually developing these applications. It's really a big benefit that you get today when you develop blockchain-based applications or using blockchain as a backend. And we don't see that same kind of benefit really coming to the middle layer, the API layer, or the end user layer as well. A lot of that has kind of been skipped in the current topologies. Okay, so what is our solution around this problem space itself? And so really it's verification, composability, modular verification as well, and are really the pillars and the foundation of the compute system that we're creating. We want to ensure that all individual components behave as expected and they have verifiable use, so that developers can build really complex systems by combining these smaller portions of the network. A lot of what this does then is we use WASM really to wrap a lot of these functions and make those functions composable together. So the product itself, so that we can kind of get into more about what Blockless is doing. It's an entire suite of products itself. So there's the developer experience tools that'll help a developer build these serverless decentralized applications. We have customizable consensus, which is really kind of big with the platform. And that's kind of where IPFS and that protocol itself comes in. So at the base of our node topology is really an IPFS gossip sub protocol that's going on. We use that protocol then to do a dynamic roll call where node workers will then fall in line to these consensus-based algorithms that are defined, whether that's PBFT, Raft, or just simply a first in, first out, fastest node worker scenario. The WASM topology then is actually all distributed currently through IPFS and Filecoin portals using the IPFS gossip sub protocol and direct connection for the execution layer itself. Really, it's supposed to be easy to use and single point distribution. We want rapid adoption of this, and that's one of the reasons why we've also gone with a WASM-based interface, is because of all of the benefits that it brings to an application like this. So our execution layer is meant to be high performance. The P2P layer is just using IPFS for discussion. There is no consensus on that layer. We actually run a separate layer blockchain that's outside of the IPFS. Right now we're using Cosmos, but we have tried it with Ethereum, and it really could be based on any L1 that's preferential. The key here is that we're augmenting whatever the L1 is with an IPFS based collection network. The nodes are really portable themselves. So because the nodes don't do anything that would be blockchainy, we're not keeping state. They really are just focused on compute. We can really run everywhere, especially with the benefit of WASM, a compile once, run everywhere with a fairly high degree of native execution. We can run on smartphones, laptops, industrial grade servers, even in the web browser. We're multi-language support, so where a lot of smart contracting may fall down is that it requires specialized languages to interact with the network. our network and our workers in our execution environment rely on a standard WASI and WASM protocol, which are all defined by specification. And so we can support any language that compiles directly to WASM. Just some of the ones that we're supporting directly, within our team are Rust, Go, JavaScript, C, C++. But obviously we could even do .NET, Python, or any of the other languages in environments that are out there. It's secure. So by nature, the WASM machine itself doesn't have an interface to it. And so a lot of what we're adding when you think about like the IPFS as being our protocol in discussion layer, we're adding on top of that then this system interface that really would control how the WASM interacts with the entire system. And all of this then is really, brilliantly put onto IPFS. So IPFS becomes the storage for our assemblies, the WASM themselves, the manifests themselves, using things like IPNS and pinning. We can then start to create an assembly structure where we pull these from IPFS then to assemble an execution strategy for a user. And that's really where we get into composable functions. The WASM assemblies are stored on a Filecoin IPFS node. We use Filecoin really because it helps the end user in that last mile. There's nothing wrong with just interacting with IPFS directly, but throwing Filecoin on top of it allows us really to tap into all of the portals that are kind of stood up around the world and really get the fast CDN kind of execution that we'd expect to happen, pulling down images in mere seconds rather than waiting for an IPFS dial. So the entire platform itself is really kind of built to, mimic what would be kind of serverless functions that you see today, but kind of offering that smart contract composability that we're used to seeing. So you can interact with several different networks based on using our SDK. This is all then executed on node topology of the developer's choice based on how trusty they want their execution environment to be. So for Web 2 developers who may not need that much trust just to get started, they could execute on a single node and get single response. And then, for the next year in Q1, we actually have planned to finalize what we call the Blockless app engine, which is actually running an x86 emulator, kind of flipping the container story on its side, if you will, and running an x86 emulator inside of a WASM machine. Instead of running a Docker and targeting the native platform underneath to abstract, we're actually going to take advantage of the fact that the WASI interface is about 95% native, no matter where we run it. And we've begun work then on writing a Linux in-machine x86 for WASM that then we can port traditional Web 2 applications, including full stack like Python, Node.js, .NET Core applications. We can boot them up in about 10 to 15 seconds, cold boot. We imagine they'll probably be used for long-running services, but we can experiment obviously with serverless in them as well. But really moving those Web 2 users to the Web 3 world. This all runs still on our distributed topology inside the node, the IPFS augmented node topology, where we're sending these WASM archives around and executing them based on the developer's chosen topology. So kind of, to quickly get into a technical architecture real quick, just to discuss how this works. The head node here would be what you would think as your IPFS boot nodes in terms of our topology. We could dial all the way up to IPFS if we want, but because of the size of the nodes at this early stage of our network, we really want to be able to measure the impact. So we run, 25 distributed nodes across the globe, 3 head nodes, 22 workers. We are using other Web3 providers, such as Run on Flux, Akash Network, to also distribute our topology currently as we go through test. This is pretty much how our system works. We do a roll call using the pub and sub. We do a roll call response using the pub and sub. We do a worker selection. Then that happens at the network level. Once the worker selections have been doled out for the pool, they do a direct libp2p dial to each other, complete work based on whatever that work requested is. If they're doing a consensus, they'll arrange into a consensus topology, pick a leader, do a vote, and then send that response back to the user. All right, so I got a quick demo I'll show here as well. All right, so I think I need to, let's see, make sure I bring this up. Oh, it looks like, give me 1 second here. It looks like I closed my.
Take your time, Derek, on the logistics. And if you could wrap up maybe the next 3 or 4 minutes, I'll give us plenty of time for David and his presentation at the very end. Thank you.
Cool. All right, so hopefully now we're looking at a video because I want to make sure the demo goes through.
Looks good.
Okay, so what we're doing here is we have a SaaS-based offering as well that kind of goes with our network. So we're hopping into the SaaS and we're going to launch a GitHub template. But what we're going to show here basically in this demo is that we're using GitHub Actions on our DX tooling that's going to build a canned Hello World WASM application. It's going to be built into WASM, archived into a car, uploaded to IPFS. And then our SaaS offering is going to get a signal that is deploying the IPFS nodes that we have for the Blockless network are going to download that WASM archive. They're going to then verify that they can execute it, send back that it has been deployed, and then we'll jump in and actually execute it. I'll speed up the video here, but just really to show, that it's real time. This all happens in under 2 minutes. So now we're deploying and finishing here, and we'll be able to hop in and grab this assembly. So here we go. We've been deployed. The job should finish and report here on the right. And now we're going to go in and we've kind of made, this is our ingress that's kind of built into this SaaS offering currently. That'll be abstracted out as part of our node topology, but it's asking hello world to be executed. It happens in about 43 seconds. We see that or 43 milliseconds, excuse me. We see that whole roll call go out. We request the nearest nodes to this worker to let us know if they can execute this function. They respond back if they meet the attributes that were requested. A worker has been selected. The function has been executed and the results were relayed back all through the libp2p library. Then they were sent to this SaaS offering, which they were transferred to this web response. Cool. And I think I've just got a couple more slides then. And so here's our roadmap that you can take a quick look at. So we're already in private alpha. We're testing with our partners. Now, as we do use case build outs and solutions for them as well. And like I said, in quarter 4 or early quarter 1, we have the app engine coming as well to start onboarding traditional web apps. And then early next year, we're looking at launching our zero knowledge WASM solution so that the compute executions are verifiable to happen, not just consensus, and as well as starting GPU support so we can start to take on some more interesting loads through distributed compute at this style. Yep. And if you have any questions, thank you so much for your time today. We have our website, blockless.network. You can follow us on Twitter. We have some hangouts there and we talk from time to time. If you'd like to see our code or contribute, you can hit us up on GitHub at Blockless Network. If anybody on this call is looking for a job or hiring, you can find us at hello@txlabs.org. And if you'd like to give it a try, reach out. We can get you allow listed to our demo. Cool. Thank you so much for your time.
Brilliant. Well done. That was I love your guys' architecture and especially the WASM WASI components. Our engineers are going to be very fascinated to see your approach because we're in the middle of that in so many different ways for Backlink now as well. So that was lovely. All right, more to come on Blockless in the Slack channel. David Anderson, are you ready? We'll hand it over to you if you're ready.
Yeah, let me bring up my slides. Okay, my name is David Anderson. I'm a computer science researcher at UC Berkeley. I got involved in distributed computing a long time ago through a project called SETI at Home. And that led to another project called BOINC, which developed a platform to let other scientists do large-scale volunteer computing projects like SETI at home. So the idea of volunteer computing is that we want to take advantage of consumer computing devices like laptops and potentially game consoles. We've actually had a project that used the processors in cars, which I think is a real interesting resource for the future. But the reason to be interested in this is that there are a lot more consumer devices than there are organizational ones. You know, a cloud might be 1 million computers, but there's a billion, or actually several billion home PCs out there. So at its peak, which was I don't know, 10 years ago, there were about 1 million computers running BOINC, and that supplied an amount of compute power that was at that point greater than the largest supercomputer in the world. And of course, home computers also have a lot of storage. The PC comes with 1 or 2 terabytes of disk, and most people don't use much of that because of cloud services. So briefly about the BOINC project, we started in 2002. We're based at Berkeley. The BOINC itself is open source, LGPL. It's on GitHub, and it has a very open architecture. It consists of a whole bunch of programs that interact through various kinds of documented network APIs, and it's easy to use it as parts of larger systems. People have built commercial systems based on it in different ways, and there's a cryptocurrency called Gridcoin that is based on BOINC. So the architecture of BOINC is that the people who are doing computing, which in general are science projects, as I should say, the focus of BOINC has been scientific computing, and that kind of breaks down into projects like SETI at home or other astronomy projects that have instruments that produce huge amounts of data and which have to be analyzed in compute-intensive ways. It's kind of one category. Another category is projects that are doing simulations, mostly molecular simulations, things like virtual drug design and protein folding and things like that, which are not data intensive, but need essentially infinite computing power. So the architecture of BOINC, it's server based. So each one of these science projects runs its own copy of the BOINC server, which is the thing that distributes jobs and provides a web interface and does a bunch of other things. The BOINC client, which is what the volunteers run on their home PCs or their phones or cars or whatever, is sort of the idea is when you run the client, you can pick from among all the available projects and decide which ones you want to participate in. And you can adjust what fraction of your resources go to each one of those projects. And what the client does then is it periodically contacts those projects to report completed jobs and to get new jobs. And it downloads the executables and the input files. And then what it does is it tries to do as much computing and as much use of storage as it can without the user of the computer being aware of that. So it keeps track of whether the user is actually at the computer and whether they're doing other computing. It looks at the memory usage to make sure that it doesn't cause thrashing. It's really kind of infinitely configurable. You can control the number of cores that it uses when you're at or not at the computer, and various preferences about how much disk space it uses. So even though BOINC started off focusing on computing, it also has a whole bunch of features related to storage. Of course, you can't do computing without storage, so it needs to store executables and input files and virtual machine images. Some of these things can add up to a lot. And it sort of allocates storage among the different projects that the client is attached to, using the resource share idea. In some cases,
David, apologies for interrupting. Just a quick question on the AV. We can see sort of a zoomed in view of the slide, but we're not able to see the entire slide. I don't know if it's the same on your side. Ah, much better.
Is that better?
Yes.
Yeah,
Thank you.
I switched to slideshow, and maybe that screwed things up.
This is just fine the way you've got it now. Thank you.
Okay. Yeah. So anyway, one of the early BOINC projects is called Einstein at Home, which analyzes data from gravitational wave detectors. And their files are fairly large, about 100 megabytes, and each file has to be analyzed with a lot of different jobs, a lot of different parameters. So the BOINC scheduler has a mechanism called locality scheduling, where when it's deciding where to send a job, it preferentially sends it to a client that already has that file, to minimize the amount of network traffic that happens. So at some point I started thinking about using BOINC just for pure data storage. And it's important to understand what the host population is like. So home computers are turned off some fraction of the time. It turns out that for a lot of computers are left on all the time, about 60% of them, but you need to take into account the other ones. In addition, people start running BOINC and then they turn it off, or the computer goes away. So there's what we call host churn, which is the arrival and departure of hosts. The lifetime of a given host has a roughly exponential distribution with a mean of about 4 months. So you can store data somewhere, but it will unpredictably disappear at some point in the future. I worked for a while on a feature that I call volunteer data archival, which had the goal of storing really large files, much larger than you could fit in a single computer, on volunteer hosts, with the idea that you could access them, but the latency of access could potentially be long, because it might take a day or two before a particular computer gets turned on again. To achieve reliability, you need to replicate the data, and of course, you have to be able to tolerate the departure of a large number of computers. So whole file replication is way too space inefficient. So this system uses what's called erasure coding, where you divide a file into a whole bunch of chunks and then generate some additional what are called checksum chunks, with a property that you can reconstruct the file from a subset of that whole collection, and you can tolerate the loss of any n of them. This has a problem in the case of the volunteer environment, which is that if you lose a chunk, you need to regenerate it, and that requires collecting the whole file in one place again and making new chunks. That's very inefficient in terms of storage and network traffic. So we use a kind of a refinement called multi-level coding, where we break the file into these chunks and checksum chunks, and then recursively divide each one of those into sub-chunks with 2 or potentially more levels to that hierarchical encoding. I developed a simulator for how the whole system would work. The simulator kind of models a host population and models the arrival and departure of hosts and the hours when they're available or not available. And it lets you experiment with different parameters for the encoding, so that you can see if you can achieve a particular target in terms of reliability, It lets you, kind of predict the amount of network traffic or or the latency that people are going to see. So I got all this working. It never actually got used for anything. But if anybody is interested in poking around with this, I'd be interested in potentially collaborating on that. So anyway, that's all I have to say. I don't know if there's a question or two.
In this case, we actually do have a few minutes left, so we can pause for questions if anyone has them. And David, I've got one question to start everyone off. I'll start with two questions, if you don't mind. One was, throughout the life cycle of BOINC, were there any major surprises in terms of how the system was architected in the past and how you may have re-architected it in the future? Or major changes you made along the way?
Well, the technology has kind of evolved gradually, essentially as hardware has evolved. We had to add support for multi-process applications. We had to add support for GPUs, and I should mention that at this point, GPUs are so much faster than CPUs that about 80% of the flops, the floating point operations, come from GPUs these days. But that was a big change to the architecture, because a GPU application, generally requires a particular version of the driver software, and there's all sorts of other considerations. So the question of whether a particular application can run on a particular computer can become very complex, and we had to add a very powerful mechanism for that. And then similarly with supporting applications that run in virtual machines. But basically, every time that Apple or Microsoft introduces a new version of their operating system, something breaks somewhere. So we at this point we're kind of in maintenance mode, but it's a very active maintenance mode.
Very good. We got time for one last question in case anyone has any questions for the BOINC. Yeah,
if I may.
Please.
So I'm super excited to be in the same call with the titans of the decentralized computing or distributed computing. So huge respect for what you did. The question is, I think we would be very much interested in what you basically mentioned. In basically this research, let's say, how do we calculate actually computational resource as a unit across all the devices that we have, GPUs, CPUs, etc., and so on. So the short question, can we sort of reach and tap into this? You said you had certain projects, certain simulations. How can we look at that and see whether we can sort of pick your brain or try to use it or to collaborate?
Just send me an email. If you go to the BOINC website, which is boinc.berkeley.edu, you can find my contact info. Yeah, I'm interested in collaborating either about storage or about computing. Yeah, there we go.
So what you mentioned regarding, so the thing that we are kind of specifically looking for, which is not exclusively, is the caching of compute state, which is something that you mentioned in your presentation.
Yeah, that's
basically a research problem that we are trying to figure out how to do that.
Yeah, BOINC doesn't do anything exactly like that, like caching of results or anything, but
well, it's not exactly caching results, but it's more like when we are running long running processes, we don't want to lose the whole process just because somebody shuts down the machine. We want to cache it and kind of do it to access this state as minimal loss, let's say this way. Yeah.
So I guess you mean checkpointing.
Yes.
If
Yeah.
one machine goes down, then another machine takes its place, like dynamically, actually.
Yeah, so BOINC, the framework allows for checkpointing. In fact, most of the applications that use BOINC have jobs that can take hours to finish, and you don't want to lose that whole time. So most of them do checkpointing. They write a file from which you can resume. BOINC does not move these checkpoint files from one computer to another. If a computer goes away forever, it just restarts the job from the beginning on a different computer. That's partly because the checkpoint files themselves can be architecture dependent. It introduces a lot of complexity. Though there are other systems like Condor, another framework for distributed computing, that do have the ability to move computing state from one place to another, but BOINC doesn't do that.
All right, thanks.
Very good. All right. And thank you again, David. It's extremely important for us to learn from people that have been doing this in the space for a while. So I very much appreciate the learnings there. And if anyone has further questions through the BOINC website, you can get David's contact information. I'll also be posting that in the Slack channel for everyone with some follow-up notes. So that will wrap us up for today. Thank you everyone for joining. This was a tremendous session, and we'll meet back again in 2 weeks for more content. Thanks everyone. Have a great day.
Thank you.
Thank you.
Bye.